Higher order algebraic theories and relative monads, Nathanael Arkor. Thank you.
Well, I'd start just by thanking the organisers for arranging this great conference. It's a really good opportunity to share our work with each other, so thank you very much. Today I'm going to be talking about some joint work with Dylan McDermott, and the sort of topic is an intersection between algebraic theory, so universal algebra and category theory, monads, and a little bit of type theory. So I'm going to start off by recapping what an algebraic theory is, and then I'm going to introduce second-order algebraic theories, which are a generalization of algebraic theories to structure that involves variable binding operations. I'm going to briefly mention a further generalization to arbitrary order algebraic theories. And then I'm going to, this will lead on to the main topic of the talk, which is how they relate to monads. So to start off with, what is an algebraic theory? Well, an algebraic theory is a categorical way to capture universal algebraic structure. So in a universal algebra, we have a set of operations, which are sort of things that take some number of inputs and return some output. So some common examples are multiplication operations, inverses, like in groups. And we can also consider multi-sorted operations like actions in a monoid or group action. So in 1963, Levier introduced the notion of algebraic theory to capture this sort of algebraic structure very generically and free from syntax. And the structure he came up with was this. You have an identitional objects functor, which preserves some structure representing the equational logic of universal algebra. So in this case, on the left, we have the free Cartesian category on a single object, which is going to represent equational logic, essentially. And on the right, we have some other Cartesian category whose morphisms are going to represent terms of an algebra and whose objects are going to represent contexts. I'm going to go into a little more detail in just a moment. So a bit more concretely, because the objects of our two categories here are the same, it means that we can see that the objects of the category on the right, curly L, are exactly the finite powers of some generating object. And so we can think of these as being contexts of n variables. And then a morphism from xn to xm, x to the power of n to x to the power of m, is going to represent a tuple of terms, each of which has n variables. So n free variables. So the other way we can think about this is that the terms are n-ary operators. And so if we consider the algebraic theory for groups, we're going to have a binary operator, so a morphism from x squared to x. And then we're going to close the operations like the multiplication, the unit, the inverses under substitution or composition in the category. And so these algebraic theories are really representing the prototypical examples of algebraic structures. Now we can form a category of algebraic theories in sort of the obvious way. We've got this commutative triangle. So functors making these identical objects functors commute. And these form a category which intuitively represent algebraic structures like groups, rings, monoids, etc. Now there's a very famous correspondence between algebraic theories and a class of monads on the category of sets. And so the idea is that in category theory, there are two core ways to talk about algebraic structure, using algebraic theories and monads, and these both have their own strengths. So in particular, the monads that are equivalent to algebraic theories, the finitary or strongly finitary monads on the category of sets. And finitary means that these monads preserve a certain class of colimits. Now, it turns out there's some technical detail here because most people talk about finitary monads on set. We're actually going to be interested in the strongly finitary monads, which are the same as finitary monads on set, but they can differ in more general settings. So really, the correspondence should be taken as correspondence with the strongly finitary monads, which preserve sifted colimits. And don't worry if you're not familiar with filtered or sifted colimits. You can just take them as some class of colimits. So this is really helpful because it gives us 3 ways to look at universal algebra. We can use the traditional syntactic equational logic for universal algebra. We can use algebraic theories, or we can use monads. And all 3 of these are helpful in different ways, and there are some results that are easier to prove in some settings than others. So it's really nice to have this sort of three-sided viewpoint. I'm going to talk about extensions to algebraic theories now. So this is a notion that's introduced by Fiori and Mahmoud in 2010. And the idea is that we want to represent type theories as sort of algebraic structures that are extended in some way. And the way we're considering them to be extended is by variable binding operators. I'm going to give some examples so you can see what I mean. So actually, the notion of variable binding operator is common in mathematics in general, not just type theory. So a very classic example is that of a differential operator. So with a differential operator, you're going to differentiate some function with respect to a variable. So here, f is assumed to contain some free variable x, and then we're going to have an operator that differentiates f with respect to x and then evaluates at some point. So anytime you see an operator that has some variable in it, that's a good sign this is an operator that fits into this framework. So another example in logic is that of universal existential quantification. So here you can see the existential quantifier quantifies over some free variable in a predicate. And in type theory, we've got the sort of prototypical example of a variable binding operator, which is the lambda abstraction operator in the simply type lambda calculus. And just to show you that these things are very common, especially in computer science, we also can consider case splitting operations. For instance, if we're representing sum types or coproducts, and we've also got fixed point operators. So these really are found in many places, even if they're not considered quite as much as algebraic operations. So again, we want to represent these binding structures in a similar way to algebraic theories. And to do that, we need to consider what the structure corresponding to variable binding operations is. So first, we're going to define this category on the left, the category that sort of provides the structural logic of the variable binding structure. So before, we took the free Cartesian category on a single object, which represents universal algebra. And now we're going to take the free Cartesian category on an exponential object. And an exponential object is one to which we can raise other objects to the power. Intuitively, this exponentiation is representing variable binding structures of a slightly higher order structure. So you can use your usual intuition for function spaces or Cartesian closed categories, for instance. But the sort of key idea is that if we look at the objects of this category, you can see they're given by these products of exponentials. And the important thing to note is that the exponents are given exactly by the objects of the free Cartesian category on a single object. So the exponents are given by the sort of arities or objects of normal algebraic structure, normal algebraic theories, and that will play a role a little later. So we can again consider a notion of algebraic theory, so an identity and objects functor that preserves the structure we're interested in. And so if you're somewhat familiar with algebraic theories, this will look very familiar. We're going to take, this time, identity and objects functors that reserve finite products and this exponential object that represents the variable binding structure. And I know I'm going quite quickly here, so you don't have to understand this definition really well. You just need to get some intuition that we're trying to capture some sort of variable binding structure, and that's going to be sufficient for the talk. So we can look a bit more concretely again at what structure these algebraic theories capture. So a morphism between objects of a second order algebraic theory are again going to represent a tuple of terms. But now the terms are not just going to have free variables, they're also going to have free metavariables. And what's a metavariable? Well, you can just think of it as a parameterized variable. So some variable that takes some inputs before being valid to use in an expression. And another way to think about this, a bit more type theoretically, is that these parameterized variables or metavariables are variables of a function type. So again, they take some inputs. And so really these are thought of as a higher order term in some sense. So to give a concrete example of a second order operator interpreted in a second order algebraic theory, take the differentiation from before. So you want to represent the operator of differentiating a function f of x with respect to x, and then evaluating at x naught. So this is going to be represented by a morphism in a category from x to the x times x into x, where the x to the x represents the f of x, which is parameterized by the variable x, and the second, the x is, so I should have used different letters here, but the second x is representing the x naught, so the point at which we're evaluating the derivative. And so if you're familiar with Cartesian closed categories at all, this will look very familiar. It's sort of a restricted notion of Cartesian closure where we don't allow all exponentials, we just have some exponentials. So again, we can form a category of these things. And so we get a category I'm calling law 2, law for Olivia. And these, very similarly, they represent a category of second order algebraic structures, like prototypical examples. And so we've got a very natural question from the start, which is, well, if in first order, in usual equational universal algebra, we can talk about a correspondence with monads, is there such a thing for second order structure where we also have variable binding operators? And this would be really useful because it would allow us to sort of use the techniques of monads from category theory to talk about these structures in a way that makes some proofs easier than just using second order algebraic theories directly or using the notion of second order equational logic. So that's sort of the motivating question for this talk. Now I'm going to very briefly mention higher order algebraic theories just to show you that there's no reason to stop at 2, and it also makes a theory much more natural. It's very natural to parameterize in an arbitrary natural number n. So again, we want to represent these structural, well, we want to represent the structure of a higher order equational logic. So a logic where we can talk about higher order operators. So we can apply operators to operators or operators to operators to operators, etc. So it's going to be a notion where we can bind variables which themselves bind variables. And it's probably a little bit hard to get an intuition for this without some examples. And if I have time at the end, I'll go through some examples, but they're less common than second order operators in general. So the structure will start to look familiar because, again, we're going to look at the free Cartesian category, but instead of taking the free Cartesian category on an exponential object, we're going to take it on an n-tetrable object, which intuitively is just an object that can be exponentiated a fixed number of times. So this means that in the second order case, it means we can form the object x to the power of x. In a third order case, we can form the object x to the power of x to the power of x, and so on. And we'll also consider omega order. So an omega tetrable object is one where we can just exponentiate it as many times as we like. And the intuition here is that a morphism in this category is going to represent an operator that takes an operator as inputs, or it might take an operator that itself takes operators as inputs. And so this is a very common thing to want to do in computer science, where you have functions everywhere and you want to pass functions to other functions. But it's slightly harder to find examples, I find, in mathematics. So the important thing to note here is that we can parameterize between the free Cartesian category on a single object and the free Cartesian closed category on a single object. So this notion of tetrability allows us to choose how much we can exponentiate in some sense. And this allows us to talk about the order of the operations we're considering. So again, we can talk about higher order, we can talk about algebraic theories of arbitrary order. So I'm going to say higher order algebraic theory to mean nth order algebraic theory for some natural number n, or for omega, meaning infinity. And this is going to be exactly the same. We're taking identity on objects functors that preserve all the structure. And again, we have a morphism of these things and they form a category. But that's not going to be so important for the rest of the talk. And again, we have this question that we had in the second order case, which is there a monad correspondence? And in the last 5 minutes or so, I'm hoping to show you that there is, in fact, such correspondence. So Before I get onto that, I just quickly need to mention this fact, which will come up later, which is that the category of nth-order algebraic theories has a very special property, which is that it's locally strongly finitely presentable. And if you've heard of locally finitely presentable categories, which is a slightly more common concept, this is a very similar notion, where we're replacing filtered colimits by sifted colimits. And the idea intuitively is that this category of nth-order algebraic theories can be built up out of colimits from some small co-Cartesian category, so a category with finite coproducts. So the idea is that really this category is very well behaved and that it's glued together out of much smaller things. And it turns out the co-Cartesian category that generates the category of nth-order algebraic theories is this category we saw before. It's the free Cartesian category on an n+1 tetrable object. So the intuition here is that the n+1th order structure is inducing all the nth order structure. And so there's some interesting relationship here between n+1th order structure and nth order structure, which will be important very soon. And to get a slightly more intuition for this, if we substitute n equals 1 into this, we get the ordinary category of algebraic theories is locally strongly finitely presentable, and in particular it's presented by the free Cartesian category on an exponential object. This is a very concrete representation of the finite presentability of this category, which is sort of very interesting. And this implies several nice properties of our category that are probably more familiar. So this means that it's locally finitely presentable as well. And it also means it's co-complete and complete. So it has all small limits and all small co-limits, which is very useful for talking about algebra, because it means we can glue things together in nice ways. Okay, so in the last few minutes, I'm going to go through the correspondence with monads. And you may have noticed that the talk title is called Relative Monads, but we're interested in a monad correspondence. And the reason this is because it's actually going to be easier to go via relative monads first and then to monads. Now you may be wondering, what is a relative monad? I've not heard of one of these before. So I'm also going to give a very quick overview of what a relative monad is. So recall that a monad is some endofunctor, so some functor from C to C, equipped with a multiplication operation and a unit operation. And these satisfy some laws essentially say that a monad is a monoid in the category of endofunctors. Now with a relative monad, we instead start with a fixed functor, which I'm calling J. And this is treated as some sort of identity, identity in quotation marks, because it's obviously not the identity functor. And so we can talk about a unit for a functor, which is just going to be a natural transformation from J, which is our identity, to some T, which will be our monad-like structure. But we can't talk about multiplication here because we can't compose T with itself because it's not an endofunctor. So we have to change the definition slightly. And it turns out that one can do this, and there's a definition of a relative monad. And when we take J to be the identity, we do recover exactly a monad. And it's not obvious from this definition that's true, but it happens to be true, and that justifies us working or treating these things as if they were monads, in a generalization of monads in some sense. And so we need to pick some J for which we're considering relative monads. And the J we're going to consider is this embedding. And so I said before that the category of algebraic theories is this co-completion under sifted colimits. And so we have a sort of Yoneda embedding for the sifted co-completion. And that's what we're going to take for our functor J. And concretely, if we take n to be 0, then the category on the left is the free co-Cartesian category on a single object. And this is equivalent to the category of finite sets and all functions. And on the right, the sifted co-completion of the category of finite sets is the category of sets. So when we consider normal algebraic theories, the functor J we're considering is exactly the inclusion of finite sets into sets. So it's very familiar. And now we have this theorem that says that n+1th order algebraic theories are equivalent to relative monads along this Yoneda embedding. And so this is the functor we're considering on the previous slide. And when n equals 0, this says exactly that algebraic theories are equivalent to relative monads for J equal to the inclusion of finite sets into all sets. And this is sort of a folklore result that's slightly less well known than the monad result. And I just need to note that there's a technical condition we need to impose here to get the correspondence, which I don't have time to get into. But this is necessary to get the actual equivalence. Now, if I could take just 2 more minutes to talk about the correspondence with monads, which I think is very satisfying. So this whole question the question we started with was, is there a monad correspondence? And you can see at the moment we're just talking about relative monads, which seem like interesting monad-like structures, but it's not quite what we wanted. So how do we do that? Well, we can start off with let's start off with, in the first order case, with normal algebraic theories. We take an algebraic theory, L, and we can generate a relative monad from the theorem on the previous slide. Now, how do we turn this into a normal monad? Well, recall that we had this Unedra embedding into the sifted co-completion, which is really just like the Unedra embedding for pre-sheaves. So that should be the intuition. And we can take the left Kahn extension of the relative monad along the Unedra embedding. And it turns out, for some nice abstract reason, that this left Kahn extension has the structure of a monad. And so we get a monad on the category SIND L1-op, which is the sifted co-completion. And so, as we said before, this sifted co-completion is exactly the category of sets. So to reiterate, when we take a first order, an ordinary algebraic theory, we generate the relative monad associated to it, and then generate the monad, we get a monad on the category of sets. And it turns out this is exactly the usual monad that is generated in the classical monad theory correspondence. So now we can repeat this pattern 1 level up. So we can look at second order algebraic theories, which have this variable binding structure. And again, we have a relative monad. And we can again take the left Kahn extension along the Unedra embedding. And now we get a monad on the sifted co-completion of the free Cartesian category on an exponential object, opt. And this is equivalent to the category of algebraic theories from the result about local strong finite presentability from before. So what does this say? It says that if we start with a second order algebraic theory, we generate a monad on the category of algebraic theories. And this pattern continues. So if we take a third order algebraic theory, we can generate a monad on the category of second order algebraic theories. Now, this may seem very abstract, and it is, because I've had to go very quickly. But the sort of gist is that we can form an equivalence with a class of monads. And if we take an n+1th order algebraic theory, we get a monad on the category of nth order algebraic theories. And these have some properties. You have to preserve some co-limits, and they have to have this linearity condition from before that I didn't have time to go into. And so the sort of moral of the story is that we can think of variable binding structure as being algebraic over algebraic structure. So this process of considering higher order operations is really an iterative procedure of adding algebraic structure to algebraic structure. And then if we take second order algebraic structure, we can add algebraic structure again and get third order algebraic structure. And this links right back to the comment I made at the start, which is that the objects of this free Cartesian category and an exponential object have as exponents the arities of the original algebraic theory, the free Cartesian category. And sort of that's a takeaway. And there are a couple of other things I don't have time to go over now, but essentially the last point I wanted to make is that we can explicitly calculate what the monad we get from an n+1th order algebraic theory is, and has a very nice representation, which is new even in the first order setting. So you actually do get some clarification about first order ordinary algebraic theories from considering this hierarchy, which is quite surprising, quite satisfying. So I'll leave it there because I think I've gone a few minutes over time, and thank you for listening.
Thank you.